Hello, my name is Scott Cheatham and I'm with the Richmond Hospital Education Program, and today we're going to be looking at a lesson on a review of quadratic functions. This would be a helpful lesson for students in Algebra 2 as they're preparing for the SOL to kind of go over an overview of the different ways that quadratic functions can be written and graphed. This would not be as helpful as kind of an introduction to it. This is more as a review lesson. On this, I'm going to ask you to do a little bit of algebraic work as well as graphing. So if you have some scratch paper, and even graph paper will be great, that's going to be helpful for you. There'll be times where I'll say, okay, go ahead and pause the presentation so you can work on some of them. And so just be ready for that. We are going to use a calculator, a graphing calculator for these. And so if you have ever used the Desmos calculator, that's going to be the one that I'm going to refer to more. Desmos has many calculators, but the most helpful one for students in Algebra 2 and beyond is going to be their graphing calculator. If you do have a TI calculator, you can use that for these. One of the benefits of the Desmos calculator is that you can click on certain points in the graph and it will actually display whatever the coordinates are. And while you can do some calculations in the TI calculator to determine those, it's a little bit more cumbersome with the steps that you have to do there on the calculate menu. I'm not going to go into the specifics of how you do that. If you aren't familiar with how you calculate a point or an intersection or a zero using the TI calculator, I would suggest looking that up before we get into this lesson. Then the first thing we want to reference is, okay, well, what is a quadratic function? You probably heard that term before. You might think of x squared, and that's really what makes something a quadratic function or a quadratic equation. Basically, a quadratic function is a polynomial with a degree of 2. Polynomial just means it's got more than one term. Now, that term might be a zero term, and so sometimes if you just had y equals x squared, we still kind of consider that to be a polynomial with a degree 2, even though it might not have any other terms. And degree of 2 just means that the highest exponent is going to be 2. And so this is kind of the general standard form that you see them. And as long as you have an x squared, all the other numbers could be 0 or 1 and not be there. But we're going to have an x squared graph. There's many things in both the real world and physics and economics that follow a quadratic path. In the beginning of algebra, you just learn and focus on linear equations, and quadratic equations and functions are the next type of function that we look into. And they get used in a variety of different ways in a variety of different circumstances. And so today we're going to, again, review how the equations can look, but then also how they can be used in some word problems. So what I would suggest that you do in your notes is to copy these 3 forms down. Don't worry if you're not sure about what those letters mean or what the terminology is. We're going to come back to those and explain in a little more detail what they are. So the first form here is standard form. That basically means that we've got an x squared, and then an x term, and then just a constant term. This is probably one of the more common ways that you'll see it. It also makes finding the vertex and intercepts a little bit more involved with how you do it. And so even though it's probably the more common one, it is a little bit tricky with how they end up calculating some of the important factors of that. But the standard form, if it's written in that, you're going to have a constant a in front of the x squared, another constant in front of x, and then constant just by itself in C. Now, vertex form is called vertex form because the vertex is very easy to pull out from that equation. We've got H and K, which are going to be the coordinates of the vertex. And this is a nice way that you can write out a quadratic equation because it's the vertex and the values of that are given right there in the equation. Now, a couple things to note. First one being A. A is not going to impact the vertex. What A actually ends up impacting is how steep or wide the quadratic equation opens up. And so that's going to be a little bit different there depending on what value A is, but it's not going to affect the vertex. The other thing is that inside the parentheses, you notice that in vertex form it's written minus H, which basically you can think of that as the x coordinate for the vertex. It's going to almost look like the opposite of whatever number is in the parentheses. So go ahead and just kind of using that idea, jot down what do you think, what would the vertex be for these three examples? So for the first one there, we do the opposite of whatever's in the parentheses there. So it is positive 4. The number outside, that's our vertical shift, and that stays the same, however it would be, in this case, 5. For the next one there, the vertex, again, we do the opposite of whatever's in the parentheses for the x coordinate, so it would be minus 2. Minus 6 is our y coordinate. And the 3 does not impact the vertex. It would impact other aspects of the graph, meaning the x-intercepts or and how steep it is, but it does not impact the vertex. Last one here, and you see that it says negative 4, and I just want to put that in there. If you actually did graph this one, you would notice that it actually is flipped over. It opens down rather than up. And so anytime that A is negative, it's going to open down, but that does not impact the vertex. Here, when you looked back at the way that it was originally written, it was just negative 4x squared. And so I wrote it here as a way to kind of emphasize that the x coordinate there, if you don't see one, it's going to be 0, vertex minus 3. So for this one, this is what we call intercept form, and that's going to be a form where basically the x-intercepts are very apparent based on the formulas. And again, you notice here that you have that minus in the intercept form, meaning that you're going to do the opposite. So it would be the opposite of whatever number's in the parentheses. For these intercepts, it really doesn't matter which one comes first. Again, if you have a negative A, it's going to open downwards. If it's positive, it's going to open upwards. And depending on how large of a number that is going to impact how steep it is. But so go ahead and write down what would the absolute values be, or excuse me, what would the x-intercepts be for these functions. So again, you do the opposite of whatever was in the parentheses. Because we're asked for the x-intercepts, I did write these as coordinates. If you just write the numbers, that's okay, but just understand that those x-intercepts are representing points. And so you want to make sure that you are recognizing that. For the third one there, it's got I put x plus 0 rather than just having the x. We are going to have generally 2 intercepts. Although sometimes it can, if the vertex is on the x-axis, we would only think of it as one unique one. But if we don't see that there, it's going to be a 0 going through the origin. So the term axis of symmetry is hopefully an idea that you're used to. An axis of symmetry really just means we're taking the graph and we're cutting it down the middle, and it's going to be symmetric on both sides, meaning the distance from any point on the left to the axis of symmetry is going to be equivalent to that mirrored image on the right. We see axes of symmetry in geometric figures and squares and stars and all sorts of things. You've probably been drawing them since you were in elementary school. But we're going to talk about, okay, well, what is the formula for that? For these quadratic functions, it's always going to be a vertical line, meaning we're always kind of x equals a number. And you see here for this quadratic graph, that kind of green dotted function is going to be the axis of symmetry here. Now, how we calculate that is going to be dependent on what type of form we have. And some of these, it's going to be a little bit obvious. Some of these, you have to do a little bit of calculation to figure it out. So let's look at the different ways. So for standard form, the first one here, this one is the one where you have to really just memorize it. You can't really calculate it or determine it without memorizing that. And so it's negative b over 2a. If you think actually back to the quadratic formula, that is the left part of the quadratic formula before the plus or minus, and that is intentional. That's not just a random occurrence. But negative b over 2a. And so that's what you would calculate for the axis of symmetry. It'd be x equals negative b over 2a. For vertex form, it's going to always go through the vertex. And so the axis of symmetry is just going to be the vertical line x equals, and then whatever the x coordinate is of the vertex. So in this case, it's our h, so almost the opposite number that you see inside those parentheses. And that's how you get it if it's in vertex form. For the last one here, for intercept form, again, a is not going to impact this. But what we are going to see is, okay, if we take the intercepts, we add them together and divide by 2, you almost can think of that as the average. If we take the average of the intercepts, the axis of symmetry is going to be right in the middle. So for p plus q, and notice that those, again, are going to be kind of the opposite values as what you would see inside the parentheses. Add them up and divide by 2, that's going to be the equation for our axis of symmetry. Now, before we start looking at how we're going to calculate the vertices, just note here that what we've calculated here for axis of symmetry, this is going to be the x-coordinate of the vertex. The y-coordinate we're going to have to determine as well, but the x-coordinate is always going to be whatever the x-coordinate is in both the vertex and the axis of symmetry. So here are 3 forms, and so let's look at what happens if we want to determine, okay, what is the vertex? So again, that formula that you have to kind of memorize, or it's the first part of the quadratic formula, is negative b over 2a. And so you see here I then have, okay, y is f of negative b over 2a, meaning whatever x was, you would have to plug it into the equation and see what your y value would be. So if that x value was 2, you would plug in x is 2 into your equation and then calculate your y from there. Vertex form, this one's really nice and easy. They give you h and k. It's right there in the formula, and so you don't have to do any calculations to solve it. For intercept form, again, the average is going to be our x value, and then you have to take whatever that is and plug it in for the x value to determine the y. So if the x value was 5, you have to plug 5 into the equation and see what y you determined. Now the last thing we're going to look at how we solve, and then we're going to do some examples, is the x-intercepts. This is sometimes called the zeros, it's sometimes called the roots, and so depending on which form we have, we're going to have to calculate these x-intercepts. Now it's important to note that x-intercepts, you might have 2, you might have 1, and you might have 0. And so depending on the way that the equation is written, you won't always have x-intercepts. But so let's look at the different ways how we would find them. So for x-intercepts, that's where does it cross the x-axis. Another way of thinking about that is what is the x values when y is 0. Because on the x-axis, y is 0 there. So for the first two here, you really just have to do some solving. You have to solve either by factoring or by the quadratic formula. You might be able to solve it using a little bit different algebraic process for when some vertex form, but you have to be able to solve when y is 0, where the x is going to be. For intercept form, the nice thing about that is it is basically the x-intercept form. So what is the intercepts that are given to you in the formula? It's just going to be the p and the q. Now y-intercepts kind of are the opposite of that idea, and that y-intercepts are where it crosses the y-axis, and so it's where x is 0. So here we're going to have to do a little bit of solving or plugging in. This one is a little bit easier for you. You're only going to have 1, and because it's a function, you're always going to have 1. And so we're going to plug in what is x is 0 and to determine these intercepts. And again here, the intercept form, you're just plugging in 0 for x and doing the calculation to determine what the y values are. So here we have 3 examples, and I want you to try and solve these first without first jumping to the graphing calculator for problems 2 and 3. For standard form, if you want to go ahead and plug that in the calculator, that's fine. But 2 and 3, we're given some very nice information here that we can pull out to be able to solve the vertex, the axis of symmetry, the intercepts. So go ahead and write these down and pause the presentation here to see if you can determine the important information and graph these equations. So this one, we're given to it this way. If we're given it in standard form, I said you can go ahead and graph this one, and we can pull out all the information that we would have here. Now, the one thing that I'll note here is that you could have rewritten this by factoring. If you look at it, what two numbers multiply to get -3 that add to get -2, would be that would be -3 and +1. And so then we could rewrite it as x -3 and x + 1 and kind of do some solving there. But at that point, it becomes an intercept form type problem. And so sometimes it's going to be helpful to rewrite something from standard form to one of these other forms, specifically intercept form, in order to be able to graph it. But here, if you have your intercepts, if you have your vertex, you should be able to sketch the graph fairly accurately. Now for finding the information for this one, we're going to start with the x-intercepts. So we're going to set that equal to 0, y equal to 0, because we want to find the x-intercepts. And when we do that, you can see the algebra over here on the side. Do note when you add the square root, you do have to add the plus or minus. That's often something that people forget. And so we end up with 0 and -4 as our intercepts. Now that's not enough to know how steep it is or how to graph it. We have to find out some more information. We have to determine, okay, well, do we have the vertex or the y-intercepts? In fact, here the x-intercept and y-intercept are the same, but if we have the vertex, then we should be able to take that with where our x-intercepts are and kind of sketch, using that idea of axis of symmetry, what would our quadratic equation look like. And because this is in vertex form, we can pull out that the vertex is -2, -12. Again, we're going to take the opposite of that number that we see inside the parentheses as our x-coordinate. The y-coordinate there is -12. And now this last one, before we look at the graph, we know a couple things. Okay, we know that we have an intercept form problem here. So I can pull out the intercepts fairly easily. But then I would need to calculate, okay, what's the y-intercept? And that's just plugging in 0 for x. When you do that, you get negative, and inside the parentheses, 0 plus 2 is 2. 0 minus 4 is -4. And it would positive 8 for your y-intercept. The axis of symmetry, again, we take the average there of -2 and +4. You end up with 1. You get x equals 1. Now for the vertex, I then need to plug 1 back into the equation to see what my y value would be. And you get the value of 1, 9. So here I've got my vertex of 1, 9, my x-intercepts and my y-intercepts, and that's going to be enough information to graph this fairly accurately. The other thing to point out there is our a value is -1, meaning this is going to open down. So here's a picture of what our graph would look like. Now, for number 4 and 5, I've given you a number of points here. Notice that it's not necessarily the vertex, but it is some intercepts. And so that's a good place to start in order to kind of work backwards from intercept form. And so go ahead and solve. Kind of give you that hint to use intercept form. Given the points that you have here, what would the values be? Now you might have to, even though you know the intercepts, you're going to need to calculate that a, and to do that you're going to need to plug in a different point that you're given. So go ahead and give these a try for 4 and 5 here. Go ahead and pause it now and use intercept form to solve for these equations. So we're given these x-intercepts are -2 and 1. And so if we're plugging those into the intercept form, again, it's going to look like the opposite numbers, so +2 and -1. Now, we don't know what a is. We can't assume that it's 1, so we need to plug in a different point. Now, you could have chosen the point 2, 8, or you know this point, the y-intercept is 0, -4. Because it's got a 0 in it, I think that's probably a little bit easier of the one to plug in, but you could have plugged in the other one as well. And so if you plug in 0 and do the algebra there, you end up getting a value of a is 2. And now we've got enough information. If you left an intercept form, that's fine. Or if you multiplied it out, that'd be fine as well. Now here we've got our intercepts of -3 and 2. And while you have a number of other points that you could plug in, again, I think the y-intercept is easier to plug in because you have a 0. That makes just life a little bit easier. So when you plug in your y-intercept of 0, 12, you end up getting a is -2. That negative makes sense because it is opening downwards. And again, if you left it in intercept form, that's exactly okay, and that's how I would say to leave it. But if you did want to multiply it out, give your answer of negative 2x squared minus 2x plus 12. Now for these last couple examples, we're going to look at some word problems and some ways that you can see these. It's something where, okay, the term show that is something we're going to see, and really that just means that they're going to give you the answer and then ask you to show the work that verifies that answer. It's kind of nice because you know what the final answer is, but you just have to make sure your work aligns with that. Now, the one thing about this equation is not written in standard form in the sense that the w squared isn't the first term, but you could rewrite this as negative w squared plus 23w minus 60. Now, because it's written this way, does not mean that you're changing what is the b and the a. For the axis of symmetry or for the x-coordinate of the vertex, it's still going to be negative b over 2a, which would be negative 23 over, now your a is negative 1. So just because it shows up the third number doesn't mean that has changed. A is whatever is the coefficient with the x squared, or in this case w squared term. Then you get 11.5. Now that's your x value. So we need to show that the maximum possible production is 72.25. And so you need to plug in the x value, which was the number of workers, and show that it ends up giving you 72.25. Because they're asking you to show it, you do need to show that work. You do need to show that plugging it in, not just write 72.25 as the answer, because you were given that to start. Now, profit is another one that can be measured oftentimes with a quadratic function, but the same idea that you can't just always measure things in a straight line. Sometimes the more things you have, it's less optimal. You're not using it as effectively. So the profit function in yen for a particular business is given by this equation, where n represents the number of units sold each week, and they make less than 3,800. Find algebraically the weekly loss for the business if it remains closed. So you got to think about, okay, if it's closed, how much is it making? The profit when 1,200 are sold, and then using a calculator, you can use the Desmos calculator, find the break-even point. Break-even means basically when is it going to start going into, we're not losing money, but we're not making money. When is it zero? You haven't lost any, but you're not making any. And then hopefully they would keep going past that to make money. So go ahead and pause here and work these out, and you can use your calculator to do part C. So if the business remained closed, that would mean that it would be producing zero units that week. So you're going to plug in for 0. When you multiply those zeros, all that's left is that minus 50,000. So it would lose 50,000 yen each week where it was closed and didn't make anything. Now you might need to use a little bit of a calculator for this one, where it's 1,200 units are sold. You plug that in for x, see what your y would be. You get 18,040 yen. Now for this one, the break-even point, that's going to be where, again, where is it 0? Where is the y value 0? And so you do have to plug that in. Now the nice thing is if you plug that in on your graphing calculator, you can click on the y-intercept and it will give you the value 926. You might have to change your zooming in order to solve for that one, but you do get 926 as your answer. All right, now the last one here is a very popular type of problem here. And so you have a rectangular fence that has a perimeter of 40 meters. Find the maximum area that it could be enclosed by this fence. Now, I give you this hint here. We're going to want to write an equation where the area of the fence that uses only one variable. So rather than using length times width, we want to think of it in terms of one variable. And then write down the dimensions of the fence that maximize the area. So again, maximize, that's going to be a vertex. So go ahead and pause it and give this one a try. So we know the perimeter, and if you think of the equation for perimeter of a rectangle, it's 2 times length plus 2 times width. And you can use that to isolate, okay, well, what would the area be? Area is going to be length times width. And so we can use those to get ourselves to an area equation here, W times 20 minus W, where we are basically at one variable in one equation. Now, when you plug this into your calculator, you get the vertexes 10, 100, meaning that the vertex, that length and or width is going to be 10. And because of the way the formula is, when you plug back in, that's also going to be your width. And your maximum area is going to be 100 meters squared. If you didn't write meters squared, I would add that in. We're talking about area here, so we want to make sure we use the right units. And for length and width, it would just be meters. Now for some extended practice, if you're still with the Richmond Hospital Education Program, we have some access to IXL. Many schools do as well. Here's 2 examples of characteristics of quadratic functions, either looking at graphs or equations. And so those would both be great practice for you as you review and get more familiar remembering the different aspects of the different quadratic equations. Thank you so much for listening to this presentation. I hope it's been helpful, and I wish you well with the rest of your school year.